The sky opens into a wide, quiet depth, and at the Milky Way's center sits a long hidden engine, Sagittarius A. Dust once hid it from view, so we first heard it in radio waves. Then astronomers tracked nearby stars as they whipped around the darkness, revealing a compact object about 4 million times the mass of the Sunday. It seemed calm compared with distant quasars, yet it became our best local laboratory for gravity. With the Event Horizon telescope, we finally captured its shadow and pinned down its size, turning theory into a measured silhouette. That image raises new questions about its spin and how it shapes our galaxy over time. If this journey helps you learn, a quick like and subscribe keeps it going. Now, let's explore what we found and what it means. Hidden behind thick clouds of dust and crowded fields of stars at the center of our galaxy sits an object our eyes cannot see, yet it holds the mass of millions of suns. Astronomers call it Sagittarius A, a supermassive black hole that helps anchor the Milky Way. It does not blaze like the bright quasars in distant galaxies. It stays faint, almost quiet, but that calm hides intense gravity and tangled magnetic fields. Space and time bend hard there. The physics is severe and simple at once. The path to understanding it is a story of looking past the glow, learning to use new kinds of light, and proving that something invisible can still cast a measurable mark. For a long time, the center of the Milky Way was out of reach. Early observers mapped nearby stars, followed the planets, and drew careful charts. Each time they aimed toward Sagittarius, the view turned muddy. There was no wall you could touch, only a haze that swallowed detail. Gas and dust drifted through that region, and the sky was so full of overlapping stars that they blurred into a white band. You could point a fine telescope and still miss what mattered, like trying to read a sign through smoke. This crowded area is the galactic bulge. It swells out from the middle of the galaxy, round and thick, bright from Earth's point of view. The bulge holds old stars and some young ones, star clusters, and clouds that glow in longer wavelengths. In front of it, and mixed within it, lies dust, made from carbon-rich grains, ices, and bits of rock from earlier generations of dying stars. Those tiny particles block visible light. They scatter it and soak it up. The result is a dark pattern across the Milky Way, like streaks on fogged glass. The light from the true center tries to reach us, but much of it fades before it can cross the last stretch of space to our eyes. The shape of the bulge made the puzzle harder. The thin disk of the Milky Way spreads like a broad pancake, but the bulge stands up from that disk. It is thicker and denser than the parts farther out. Stars crowd together there. Their light piles up from every direction, so signals overlap. Dust mixed into the scene adds more confusion. The information is present, yet it is masked by too much of the same kind of light. What we needed was a different window. For centuries, people could admire the spiral arms from the outside, chart some lanes of dust, and trace star clusters, yet still not know what sat at the heart. Some even asked whether a real center existed at all. Was the galaxy turning around something? Or was it more like a loose swarm with no anchor? Ideas came and went without strong tests, because the tools of the time were tied to visible light, the same narrow band our eyes evolved to use. That band is rich for nearby things. It is poor when dust stands in the way. This limits how the sky appears. Visible light cannot easily pass through the densest clouds between stars. When you look only in that band, you see an edited version of the galaxy. Early astronomers did not yet know about interstellar dust. Many thought the sun sat near the center because the star counts looked roughly even in many directions. The truth was less flattering. The dust was fooling them, blocking light from the real center and giving the illusion of balance. The maps reflected the limits of the method rather than the structure of the Milky Way. In the 1700s and 1800s, William Herschel and others tried a simple approach. They counted stars in different parts of the sky to infer shape. More stars, they reasoned, meant a thicker part of the galaxy in that direction. Fewer stars meant thinner parts. It was a bold plan with a quiet flaw. Dust and gas were not in the model. When their counts swung high or low, they read structure into the numbers that also carried the imprint of hidden clouds. They were skilled, and their instruments were strong for the time, but the sky was speaking in a code they could not yet break. The code began to open in the 20th century. Scientists built detectors and telescopes for kinds of light that our eyes cannot see. Infrared light, which has longer wavelengths than red, can slip through dust more easily. Radio waves, which are even longer, pass through many clouds with less loss. Both carry real information about objects that do not shine strongly in visible light. The way forward was to look with these tools and to place them above some of the blur. Infrared observatories were built on dry, high peaks and later flown on aircraft and placed in space. Receivers for radio astronomy spread across valleys and plains. Together, they started to lift the curtain. Through infrared eyes, the bulge lit up. Stars that looked dim or invisible in visible light came into view. Clusters stood out. Gas near the center glowed. Paths of dust became layers you could peer between. What had looked like a blank patch revealed a busy scene with motion and heat. The center was not empty. It was active, and it was nearby in cosmic terms, about 26,000 light-years from us. With patient surveys, astronomers began to trace the layout and to look for signs of something compact and heavy at the core. A key step came from radio work that did not start as astronomy at all. In the early 1930 seconds, Carl Jansky, an engineer at Bell Telephone Laboratories, tried to find the cause of static that spoiled radio calls. He built a rotating antenna on a wooden turntable so he could scan the horizon and the sky. It listened around 20.5 megahertz, a frequency with a wavelength of about 15 meters. Jansky logged months of data. He traced some noise to local storms and some to distant lightning, yet a steady hiss rose and fell on a rhythm of one cycle per day. At first, that suggested the Sunday. The timing was off by a little. The peak arrived about 4 minutes earlier each day. That small shift mattered. A solar day is 24 hours. A sidereal day, the time it takes Earth to turn once, relative to the stars, is about 23 hours and 56 minutes. The daily advance in the peak fit the sidereal clock, not the solar one. The source was not tied to the Sunday. It was fixed among the stars. When Jansky traced the direction on the sky, it pointed toward the heart of the Milky Way. Without aiming for it, he had found radio waves coming from our galaxy's center. It was the first confirmed radio signal from beyond the solar system. An engineering task had opened a new door. At the time, few in astronomy knew what to do with this result. Optical work still dominated. Jansky did not continue. His antenna was taken down, and Bell Labs moved on. Yet the idea took root. In the late 1930 seconds, Grote Reber, a radio engineer and avid amateur observer, read Jansky's report and decided to try on his own. He built a 31-foot, about 9-meter metal dish in his yard with a receiver at the focus and began to chart the radio sky. Working mostly alone, he confirmed the bright radio direction near Sagittarius and produced the first radio map of the Milky Way. In that map, the galactic plane glowed, and the center stood out. During the 1,940 seconds and 1,950 seconds, more groups joined in. Wartime advances in radar made better receivers and antennas possible. New instruments tuned to a range of frequencies from tens of megahertz up to gigahertz revealed a sky full of sources that did not look special in visible light. Supernova remnants, where old stars had exploded, shone in radio. Clouds of ionized hydrogen, called H2 regions, sent out distinct signals. The center region grew brighter in these maps. The message was simple. If you listen in the right band, the hidden parts of the galaxy speak clearly. This shift in technique changed the questions people could ask. With infrared and radio data, astronomers could follow gas lanes that spiral inward. They could pick out compact knots that hinted at violent processes near the core. They measured how much dust dims starlight, a process called extinction, and they corrected for it. They estimated distances and motions with more confidence. Bit by bit, they set up the tests needed to prove whether a heavy, compact object sat at the center. Methods, not a single machine or hero, made the breakthrough possible. Dust blocks short wavelengths, so astronomers used longer ones, like infrared and radio. Crowded fields hide single stars, so they built sharper infrared cameras and learned to separate points of light with careful analysis. Signals were faint, so they observed longer and linked many radio dishes across Earth in interferometry, a technique that lets a network act like one giant telescope. Each upgrade pulled more detail from the same patch of sky. These tools did not appear overnight. They grew step by step. By the 1,960 seconds, radio telescopes were already sensitive and precise enough to redraw our picture of the Milky Way. Bigger dishes and quieter receivers revealed gas clouds and the shells of old supernovas, and maps began to show bright knots in other galaxies. One compact source, near the constellation Sagittarius, stood out. It stayed narrow on the sky, instead of spreading like a nebula. It was strong and steady, sitting right at the Milky Way's dynamical center. Observers tagged this point as Sagittarius A, the asterisk marking a special, spiky radio source that flickered and flared. To cut through the last confusion, astronomers turned from pictures to motion. They tracked individual stars very close to the center, measuring tiny shifts year after year as each star traced its path. Orbits reveal mass. Those paths would tell how heavy the unseen object was and how small a space it occupied. It was a clean test of gravity in a hard place made possible because, starting decades earlier, people had learned to look with kinds of light that dust cannot easily hide and to combine many instruments into one clear view. Images and spectra had taken us to the threshold. To decide what the compact source truly was, only the measured motion of nearby stars would do. The signal's behavior did not match common radio objects. It wasn't the expanding ring of a fresh supernova remnant, nor a broad cloud warmed by nearby stars. Its spectrum, the way brightness changes with frequency, hinted at fast electrons spiraling in magnetic fields. Synchrotron radiation. A useful clue, but not decisive, since many sources can produce it. The deciding evidence would be stellar motion. If a very heavy object sat at the center, nearby stars would move as if tugged by a compact mass. Measuring that pull required tracking their orbits with precision. The challenge was distance and dust. The galactic center is about 26,000 light-years away. Stars there can move at thousands of miles per second, yet their full paths take years to decades. Visible light cannot get through the thick clouds between us and the core. Astronomers needed infrared, which has longer wavelengths that slip past dust more easily. They also needed stable platforms and code detectors to cut down noise from Earth's warm atmosphere. Progress came in layers. Teams first carried infrared instruments on high-altitude balloons and aircraft to rise above the wettest air. Observatories on very high, dry mountains added the next step. Sites like Mauna Kea in Hawaii and the Atacama Desert in Chile offer thin, stable air with little water vapor. From those summits, the inner galaxy began to look busy instead of blank. Regions that appeared dark to the eye revealed clusters of stars, lanes of warm dust, and arcs of gas shaped by gravity and radiation. The center was crowded and active. Space missions confirmed how much the atmosphere hides. In 1983, the infrared astronomical satellite, IRAS, made the first full-sky infrared map. It was not built to zoom in on the very core, but it showed that dusty regions glow with hidden structure. Whole star-forming complexes lit up. Warm dust and strange sources appeared where optical images were thin. IRAS proved that leaving the atmosphere behind changes the story. It set the path for colder, sharper instruments to follow. The Spitzer Space Telescope, launched in 2003, took that path. With cryogenic detectors, Spitzer could pick up faint heat from across the Milky Way. It worked in several infrared bands, each sensitive to different temperatures and molecules. Toward the center, Spitzer traced crowded star fields, twisted filaments, and curving dust lanes that funnel gas inward. While it could not resolve the tiniest scales right next to the compact radio source, it mapped the environment and highlighted where gravity is strongest. It showed that the inner few hundred light-years contain young star clusters, shocked gas, and magnetic structures pointing to a restless core. Ground-based resolution improved in parallel. At radio wavelengths, very long baseline interferometry, VLBI, linked dishes across continents, shrinking the effective beam to a pinpoint and fixing the radio source's position with extreme accuracy. At infrared wavelengths, adaptive optics counters the blur from atmospheric turbulence. Instruments measure how the air distorts starlight, then flex a thin mirror many times per second to cancel that distortion. On large telescopes, this brings images close to the sharpness set by the mirror's size. With adaptive optics, astronomers could finally separate individual stars within a light day of the center. Two groups built long records of those stars. In Chile, Reinhard Genzel's team used instruments at the European Southern Observatory, including the Very Large Telescope. In Hawaii, Andrea Gez's team used the twin Keck telescopes on Mauna Kea. Each group created precise star catalogs with positions measured to tiny fractions of an arcsecond and returned year after year to add points to each track. The stars they followed are called stars because they lie in the Sagittarius field. They move on tight, fast orbits that feel only the gravity of the central mass. One star, S2, also called S2, became key. Its path is a long oval that takes about 16 years to complete. At the closest point, S2 dives to a distance roughly the size of our solar system and then swings back out again. By measuring its position on the sky and its speed from the Doppler shift of its light at many points along the way, both teams could fit an orbit and read off the mass that drives it. The answer was about 4 million times the mass of the Sunday. Just as important, that mass had to be confined to a very small volume. If it were a cluster of normal stars, neutron stars, or white dwarfs, it would spread out or collapse quickly. Models showed that such a cluster would not stay so compact for long. A single, supermassive black hole fit the data and stayed stable. As instruments improved, more effects came into reach. Near S2's closest approach, its light showed a small extra redshift beyond what Newton's gravity would predict. This shift matches general relativity, which says time runs a little slower in stronger gravity and light loses a bit of energy as it climbs out. The observed change agreed with Einstein's equations within the uncertainties. Subtle twists in the orbit's shape, expected from the curvature of spacetime, became measurable with continued tracking. Each added point tightened the case. Radio measurements supplied direct size limits. Sagittarius A, often shortened to SCR-A, flickers on timescales of minutes to hours. An object cannot change overall brightness faster than light can cross it, so those rapid variations imply a very small emitting region, only a few times larger than the event horizon. VLBI nailed the source's position to the exact dynamical center defined by the star's orbits. It also revealed short-term structure in the radio emission that fits hot, magnetized gas close to the black hole. Other wavelengths filled in context. X-ray satellites saw brief flares from the core, consistent with pockets of gas heating up as they spiral inward and then cooling. Mid-infrared observations traced warm dust that outlines cavities carved by past activity and strong stellar winds. Spectroscopy across infrared and optical bands measured line-of-sight speeds of stars and gas, and those speeds matched the motion seen in the plane of the sky. When positions, velocities, and timing all point to the same mass and the same compact scale, the model becomes tightly constrained. The toolbox was broad because the problem was layered. Dust blocks visible light, so astronomers used infrared, crowding blends starlight. So they sharpened images with adaptive optics and built long time series to separate paths. The central object is too small for any one telescope to resolve, so radio astronomers linked dishes across Earth. The region is dynamic, so teams observed over decades to watch complete arcs. Calibrations improved, reference frames were tied together, and detector drifts were measured and removed. Step by step, the remaining uncertainty shrank. The stellar dance that revealed the hidden mass became one of the clearest results in modern astronomy. With the right tools, the motion of a star can be measured to a tiny slice of angle called an arcsecond, and even to thousandths of that unit small, but enough if you watch for years. In the 1,990 seconds, 2 long campaigns began. One team, led by Reinhard Genzel at the Max Planck Institute, worked from Chile. Another, led by Andrea Ghez at UCLA, worked from Hawaii. Using large ground-based telescopes with advanced infrared cameras, they pierced the dust and tracked individual stars near the Milky Way's core, aiming to read gravity directly from their paths. As positions and velocities accumulated, orbits tightened into view, and the method turned motion into mass. By the early 2000s and into the 2010 seconds, the picture had weight. A compact, bright radio source sat exactly at the dynamical center, and stars traced clean orbits around a single, heavy point mass. The mass was about 4 million suns, confined to a region smaller than our solar system. Alternate ideas like a cluster of dark remnants failed stability tests. Relativistic effects appeared where expected. Infrared maps showed lanes that can feed gas inward, while radio and X-ray data captured brief outbursts near the edge of the abyss. Taken together, the simplest, consistent explanation across all methods was a supermassive black hole at the heart of the Milky Way. The atmosphere fought them at every turn. Air is in constant motion. Layers at different temperatures bend light in shifting ways, so a star's image swells, jumps, and blurs. To overcome this, the teams used adaptive optics, a method that measures the blur in real time and cancels it with a flexible mirror. The system needs a bright reference point. Sometimes a natural star is close enough, but often it is not. In that case, a laser is fired into the upper atmosphere. It excites a thin layer of sodium atoms about 90 kilometers up, creating an artificial guide star. Sensors read how that dot is distorted on the way back down. Computers then command the mirror to change shape hundreds of times per second, pushing against the blur and sharpening the scene. The first time this was applied to the galactic center, a messy glow broke into a field of pinpoints. The core was no longer a smear. It was a crowd of distinct stars. Those stars were not slow. Near the center, some moved at more than 5,000 kilometers per second. That speed could carry you from Earth to the Moon in a little over a minute. They whipped around a point in space that gave off almost no light. The teams gave these targets short names, often beginning with S for the Sagittarius field. Each year they returned and added new positions to each star's track. They also took spectra, which means splitting the starlight into its colors to find tiny shifts. When a star moves toward us, its lines shift slightly bluer. When it moves away, they shift redder. This Doppler effect reveals speed along our line of sight and complements the motion measured on the sky. With two components of motion and time, you can fit an orbit and weigh the object that tugs on the star. One star dominated the early story. It is known as S2 or S2. S2 follows a stretched oval path, an ellipse around the dark center, completing one full loop in about 16 years. At its closest approach, the star dives inward to a distance comparable to the size of our solar system, then swings back out. As the observations piled up, the shape and timing of its orbit sharpened. Both teams solved for the mass needed to keep S2 on that course. The answer clustered around 4 million times the mass of the Sunday. The implied size of the central object was tiny compared with that mass. A normal cluster of small, faint objects could not stay that compact. It would puff up or collapse in a short time. A single supermassive black hole fit the data, and it would remain stable. Even small details matched that picture. Near closest approach, S2's light showed an extra redshift beyond the Newtonian expectation. General relativity explains this as gravitational redshift. Light loses a bit of energy as it climbs out of a deep gravity well, so its color shifts slightly toward the red. The timing of the orbit also hinted at the curvature of space-time, producing subtle changes in the path that only show up with careful, long-term tracking. These effects are small compared with the main pull of gravity, but they become measurable when you know exactly where the star is, night after night, year after year. The work depended on more than sharp images. It required steady reference frames so positions could be compared across different seasons and even different instruments. It required exact calibrations of scale so that a pixel on a detector always meant the same angle on the sky. It needed models of how dust dims light and how starlight spreads in a crowded field. The teams built catalogs of reference stars, corrected for tiny drifts in detectors, and cross-checked their results by switching methods. They measured proper motions across the sky, and radial velocities, motions toward or away from us. When both point to the same mass, the case tightens. Results arrived in stages. In 2002, the UCLA group published the first full orbit of S2. In 2008, the Max Planck group presented a refined solution with more data points and improved instrumentation. The numbers agreed within small uncertainties. Independent analysis from different telescopes, different cameras, and different pipelines led to the same mass and the same location for the compact source. More stars joined the roster. Some had longer periods. Some reached even closer on their inward swing, all lined up with a single, heavy object at the same spot as the bright, compact radio source known as Sagittarius A. As the 2010 seconds began, the instruments grew more precise. Adaptive optics matured. Laser-guide stars became routine rather than experimental. Measurements reached accuracies of 1,000th of an arcsecond and better. That is like judging the width of a human hair from several kilometers away. With such precision, tiny departures from simple ellipses could be seen and modeled. The orbits still screamed point mass, but now they also carried the finer print of relativistic effects. Each pericenter passage, the moment a star loops closest to the center, turned into a stress test for gravity. Radio astronomers added their own constraints. The compact source at the center, SGIA A, flickers and flares on timescales of minutes to hours. An object cannot brighten or fade faster than light can cross it, so the fastest swings in brightness mark an upper limit on size. Those swings are consistent with an emitting region only a few times larger than the event horizon of a 4 million solar mass black hole. Very long baseline interferometry pinned the radio source to the same location defined by the star orbits, within tiny errors. Together, the infrared and radio data closed the gap between heavy and small and a black hole. Other wavelengths filled in the setting. Space-based X-ray telescopes caught short, faint flares from the core, likely brief episodes when pockets of gas heat up as they spiral inward. Mid-infrared images traced warm dust shaped by winds from massive stars and by older outbursts. Spectroscopy across near-infrared bands measured how fast stars and gas approach or recede, and those speeds matched the motion seen on the plane of the sky. When positions, velocities, and timing all agree on the same mass and the same compact scale, alternative ideas fall away. The method behind all this is direct and sturdy. Gravity tells matter how to move. Measure motion well, and you can weigh the source of gravity. The difficulty lies in the doing. Cutting through dust, defeating blur, holding a stable frame, building long baselines of data, and checking many possible errors. The payoff is that you do not need to assume the object shines a certain way. You do not need to rely on models of how gas behaves close to a hot source. You simply let the stars be test particles and read the mass from their paths. By the middle of the decade, results from different teams and instruments agreed. A compact, radio bright point sat at the exact dynamical center. Stars around it traced tight ellipses. The central mass was about 4 million suns, packed into a volume smaller than our solar system. The orbits showed small shifts expected from curved space-time, and the rapid radio flicker pointed to a size near the event horizon. Each new measurement left less room for other ideas. What remained was a supermassive black hole, confirmed not by distant jets or vague glow, but by the measured dance of nearby stars and the timing of their closest passes. With that core result in hand, the next step is to place it within the black hole family. Black holes started as a simple idea. Gravity so strong that not even light can escape, but nature makes them in several ways. and those paths shape how they look and grow. The compact mass at the Milky Way's center, Sagittarius A, belongs to the largest class, supermassive black holes. Like all black holes, it has an event horizon, a boundary of no return. How it reached its size, how it feeds, and how it behaves can be compared with other kinds, and those comparisons give context for what our galactic center is and what it is not. The smallest well-established group is the stellar mass black holes. These form when very massive stars run out of nuclear fuel. A star holds itself up by balancing the inward pull of gravity with the outward pressure from fusion in its core. When the fuel ends, that pressure drops. The core collapses. If the core is heavy enough, the collapse does not stop at a neutron star. It continues into a black hole. The leftover mass can be a few times the sun's mass, sometimes more than 10, and the size of the event horizon can be only a few miles across. These black holes do not glow on their own, but if they sit in a pair with another star, they can pull gas from their partner. The gas forms a hot, fast disk called an accretion disk. Friction and magnetic forces in the disk heat the gas until it radiates X-rays. That is why many stellar black holes were first found by X-ray satellites. The light flickers as the flow changes, and those changes tell astronomers about the size of the innermost orbits. In our galaxy, dozens of such systems have been confirmed, and many more are likely hidden among faint sources. A step up in mass sits the intermediate mass black holes, which range from a few hundred to a few 100,000 solar masses. They are harder to confirm because they are too heavy to form from a single dying star and too light to power the brightest galactic cores. Several clues point to them. In dense star clusters, the motions of stars toward the center can hint at something more massive than any single star. In a few cases, bright flares from the centers of dwarf galaxies suggest a black hole that is bigger than stellar mass, but not yet supermassive. Gravitational waves, ripples in spacetime, detected by instruments like LIGO, have revealed mergers of black holes up to a few dozen solar masses, and as the detectors improve, they may catch fusions that produce hundreds of solar masses. The leading ideas for making an intermediate black hole include repeated mergers of stellar black holes inside crowded clusters and the slow, steady eating of gas and stars over long times. They are interesting not because they are common, but because they may explain how the giants begin. Supermassive black holes are the giants. They weigh millions to billions of suns, some power-blazing quasars in the distant universe, outshining their host galaxies as they swallow gas at a high rate. The engine is the same accretion disk as in the small systems, but scaled up with stronger magnetic fields and faster flows. In many active galaxies, collimated jets, narrow beams of particles moving near the speed of light, shoot out from the poles and can stretch for thousands of light years. These jets and winds can push back on the gas in the galaxy, a process called feedback, which can slow or stop star formation in the host. Sagittarius A sits at the light end of the supermassive class, around 4 million solar masses, and today it is quiet. Quiet does not mean empty. It means the flow of gas into the black hole is low most of the time, so the disk is dim. From time to time it flares in infrared, radio, or X-rays for an hour or so, likely when a clump of gas heats up near the innermost orbits, or when magnetic fields reconnect and release energy. The low activity removes the bright glare that would otherwise hide nearby stars, which is why the orbits used to weigh it could be tracked. There is also a proposed class that lives in theory and in the very early universe, primordial black holes. The idea is that tiny, Brief spikes in density just after the Big Bang could have collapsed straight into black holes without any stars involved. Depending on the size of the spike, the resulting black hole could be as small as a mountain or as heavy as a star. Astronomers have searched for signs of such objects by looking for brief lensing events, moments when a compact mass passes in front of a more distant star and magnifies it, or by checking how their evaporation, predicted by quantum theory for small black holes, would glow in high-energy light. So far, there is no clear detection, but the searches place limits on how many of these objects could exist. The idea remains useful because it tests how structure formed in the first moments and because it offers one of many checks on the nature of dark matter. Placing Sagittarius A among these types highlights what makes it unusual. It is a supermassive black hole that is close enough for us to resolve the motion of individual stars in its grip. It is faint enough at most times that the bright background does not overwhelm those stars. The gas near it is hot and thin, so it likely flows in through a mode called radiatively inefficient accretion, where much of the energy stays in the gas rather than shining away as light. That helps explain the low average brightness. Yet the gravity is the same gravity that rules the brightest quasars. The mass sets the scale. The event horizon radius grows with mass, and the time scales for orbits near the horizon grow with mass too. At 4 million solar masses, one orbit near the innermost stable circular path takes minutes, not milliseconds, as in a stellar black hole. That slower clock lets instruments watch changes play out in real time. The name Sagittarius A carries a piece of history. In the 1,970 seconds, as radio astronomers mapped the crowded central sky, they labeled the first prominent source in the constellation Sagittarius as Sagittarius A, following a simple catalog style that moves through letters as new sources are added. Within that region, Bruce Bellick and Robert Brown isolated a compact, spiky point right at the center. To mark its special nature, Brown added an asterisk, borrowing the symbol used in atomic physics to flag an excited state. The star-shaped symbol did not mean the object was a star. It meant the source was distinct and energetic. The tag was informal at first, but it caught on because it was clear and memorable. Over time, Sagittarius A became the standard way to refer to the compact radio source at the Milky Way's dynamical center. The asterisk at the end makes a small, tidy irony. Spoken aloud, it sounds like star, yet the object hides stars by bending their light and pulling on their paths. The name fixed an invisible point on our maps and gave people a way to discuss the same place across different wavelengths and methods. It sits alongside a mix of other naming styles in astronomy. Some names come from ancient words passed down through cultures. Others are simple catalog numbers that tell you which list found them and in what order. In the radio and X-ray bands, where many sources are not visible to the eye, the names often carry the constellation and a short code. The aim is not poetry. It is to keep track as the lists grow. Comparisons across the black hole types sharpen working ideas about growth. A stellar black hole can double its mass by taking gas from a companion, but it will stay in the tens of solar masses unless it merges with others. An intermediate black hole, if it exists in a dense cluster, can sweep up neighbors, stir the cluster, and sink toward any larger mass at the center. A supermassive black hole can build itself early by direct collapse of a massive, metal-poor gas cloud in the young universe, then keep growing by eating gas, swallowing stars, and merging with other black holes when galaxies collide. The details are active research, yet the broad picture is consistent. Small seeds form first, environments feed them, at rates set by local conditions, and mergers add steps. Sagittarius A likely followed a path that included steady feeding and at least one merger in the Milky Way's past. But today, it sits in a calm patch with only a thin, hot trickle of gas. Understanding how these classes differ also helps explain why the centers of galaxies can be so influential. When a supermassive black hole is active, it can heat or expel gas from the central regions. That changes how many new stars can form. Even after the active phase fades, the history of those outflows can be read in arcs of warm dust, shells of ionized gas, and the motions of stars that formed in bursts. In a quiet phase like the one around Sagittarius A, the feedback is gentler, driven by winds from massive stars and by occasional flares. That quieter setting helps isolate pure gravity tests, such as the orbital shifts measured for stars, while still allowing studies of how magnetic fields thread the inner gas and how turbulence moves energy around the flow. Gravity sets the stage. Gas brings fuel. Magnetic fields and rotation act like gears that move angular momentum outward so matter can fall inward. The light we see depends on how much fuel arrives and how efficiently the flow turns energy into radiation. Small black holes flicker fast. Supermassive ones change slowly. In every case, the event horizon is the point of no return, and the shadow, the dark patch against glowing material, scales with mass and spin. The object at our center is modest by quasar standards, yet close enough to study in detail. Its quiet nature removes glare, and its mass sets timescales we can follow. Its name ties decades of radio, infrared, and X-ray work to one compact source in Sagittarius. With that local picture clear, the view widens. Across the sky, most galaxies' spirals, ellipticals, even many irregulars, host a giant black hole at their core. The first clues often came from galaxies with very bright centers, where gas and dust fall inward quickly, heat up in a disk, and release huge amounts of energy. These are active galactic nuclei. Their output is far beyond what normal star clusters can make. The simplest, consistent cause is a supermassive black hole feeding. Quasars, visible from billions of light years away, follow the same logic. Steady power and extreme brightness from matter spiraling in and turning gravity into light. Once the tools were ready, astronomers checked quieter galaxies. They looked for fast motions near the center, for gas turning in tight curves, and for stars on orbits that only a heavy, compact object could drive. Time after time, the signs were there. Some central black holes were active, many were not. Dormant ones still left a clean fingerprint in the motions of nearby stars and clouds. Soon the burden of proof flipped. Instead of asking whether a given galaxy had a central black hole, the better question was, why this pairing seems almost universal. One line of thought is that black holes and galaxies grew up together. In the early universe, large, metal-poor gas clouds could have collapsed directly into massive black holes instead of breaking into many stars first. Those early seeds would then grow by eating gas and merging with other black holes as galaxies collided. Another idea starts with the first generation of very massive stars. These short-lived giants could end in heavy black hole remnants that later merged and fed. Either way, growth is not random. A tight link appears between the mass of the central black hole and the mass of the galaxy's bulge, the dense central region of stars. Across many systems, big bulges go with big black holes. The relation is not perfect, but it is surprisingly narrow, which hints at a feedback loop. When the black hole feeds hard, winds and jets can push gas outward and shut down star formation. When the galaxy builds stars in bursts, some of that activity can guide more gas toward the center, feeding the black hole. Cause and effect run both ways, knitting the histories together. Timing makes the puzzle sharper. Telescopes have found quasars powered by billion solar mass black holes when the universe was less than 1 billion years old. That is fast growth on a cosmic clock. To reach such masses that early, the seeds must have been heavy at birth, or the feeding must have been very efficient, or both. Frequent mergers could help. So could brief periods of near maximal feeding, when gas piles in as fast as physics allows. The details are still being worked out, but the headline remains: supermassive black holes can form and grow quickly. Sagittarius A is small compared with those monsters, yet it fits the same pattern. Our spiral galaxy hosts a central black hole of about 4 million suns, modest by quasar standards, but exactly in line with the idea that galaxies and central black holes travel together. Comparisons fix the scale. The black hole in the giant elliptical galaxy M87, first imaged in silhouette in 2019, weighs billions of suns, more than 1,000 times heavier than Sagittarius A. Its event horizon dwarfs our solar system, yet it is not the record holder. In the galaxy cluster around Holmberg 15A, estimates point to a central black hole of roughly tens of billions of solar masses. Step higher, and you reach TON 618, a quasar whose black hole is estimated around 40 billion suns. In mass, that is as if 10,000 Sagittarius A objects were combined. The event horizon of TON 618 is so large that a beam of light would take about a week to cross it. For Sagittarius A, that crossing time is on the order of a few dozen seconds. Numbers like these stretch everyday intuition, but they underline how wide the family truly is. Size alone does not tell you how dangerous a region is. Gravity weakens with distance. Far from the center, a supermassive black hole pulls with the same strength as any other object of the same mass. The differences show up close in, where the event horizon and the inner disk lie, and in how much gas is falling inward. Sagittarius A is in a quiet state. It usually sips gas rather than gulping it, and the flow is hot and thin. That makes the system faint, with occasional flares in radio, infrared, or X-rays when small clumps heat up or magnetic fields snap and reconnect. TON 618 is in a very different mode. As an active quasar, it is devouring matter quickly. The disk blazes and outshines entire galaxies. The flow can also drive jets narrow, fast beams of particles launched along magnetic field lines that sprint out at nearly the speed of light. These feeding differences change how the host galaxy evolves. Strong outflows can heat or sweep gas from the center, reducing the raw material for new stars. Quieter phases allow gas to settle and form stars over longer times. Clues suggest that Sagittarius A was more active in the past. On very large scales above and below the Milky Way's plane, gamma-ray maps show 2 huge lobes known as the Fermi bubbles. Their edges are crisp, like the rims of old outflows. They may be the relics of a past episode when our central black hole fed harder and launched energy into the halo a few million years ago. X-ray and microwave observations show related features, adding weight to the idea that our quiet nucleus has had bright phases and may again. Spin adds another thread. A black hole's spin describes how fast it rotates. Spin changes the innermost orbits, affects how efficiently the disk can turn gravitational energy into light, and helps set the strength and direction of jets. Measuring spin is difficult. It requires careful modeling of the glow from gas very close to the event horizon, or the shape of the shadow in high-resolution images. For some giants, like the one in M87, evidence points to rapid spin, near the upper limit allowed. A fast spin can act like a turbine, tapping rotational energy to help launch jets through magnetic fields. The spin of Sagittarius A is still being pinned down. Early results allow a range, but the coming years of high-resolution imaging and timing should narrow it. Growth paths vary with environment. A black hole can gain mass by swallowing gas, by disrupting and eating stars that wander too close, and by merging with other black holes. Our galaxy has merged with smaller neighbors many times. Each merger can deliver a central black hole of its own. Over long periods, dynamical friction, gravitational drag from stars, and dark matter drains the orbital energy of the smaller black hole, bringing it to the center, where the pair can eventually merge. That process adds to Sagittarius A's mass in steps. The same processes, scaled up and repeated in rich environments, can produce the extreme masses seen in giant ellipticals and in the brightest quasars. Looking ahead on long timescales, the Milky Way and Andromeda are drifting toward each other. In several billion years, they will collide and merge. Their central black holes will sink to the common center and eventually coalesce. The result will be a heavier central black hole, likely several times the mass of Sagittarius A today. During the merger, gas will be stirred and funneled inward, possibly lighting the nucleus for a time. Afterward, as the new galaxy settles, the central engine may quiet again. The spread of environments helps explain the range we see. Sagittarius A lives in a spiral galaxy with a mix of old and young stars and a moderate gas supply. Its neighborhood is busy, but not extreme. Ton 618 blazes from a more violent setting, with steady fuel driving a bright, active core. M87's black hole sits in a giant elliptical at the center of a cluster, with access to vast gas reservoirs and frequent interactions. Holmberg 15A lies in an even denser hub, where many galaxies have been digested. In each case, local conditions, fuel, mergers, and the history of star formation shape how the central black hole grows and how it shines. Across all these systems, a few simple rules keep showing up. Gravity sets the pace. Fuel feeds the engine. Magnetic fields and rotation help move angular momentum outward, so matter can fall inward. When fuel is scarce, the flow is hot and inefficient, and the light is weak. When fuel is abundant, the disk glows, winds rise, and jets can form. The central mass grows either way, faster in feast than in famine. The broad relation between black hole mass and bulge mass, and the sight of giant black holes in young quasars, tell us that this dance between galaxies and their cores has been going on since early times. Sagittarius A sits as a nearby case study, modest in mass, quiet most days, yet part of the same pattern that links humble spirals, bright quasars, and the largest galaxies in the universe. Sagittarius A is massive, yet quiet, because its fuel supply is thin and uneven. A black hole does not slow with age, it simply follows the supply. When gas and dust drift inward, gravity pulls them toward the center. Close in, the flow heats up and becomes a hot plasma. If the inflow is steady and dense, the disk shines strongly and the system looks like a quasar. If the inflow is weak and patchy, much of the gas never reaches the event horizon. It stalls, loses some energy, and is lifted outward by pressure, magnetic turbulence, and winds. Models call this a low rate or radiatively inefficient flow, meaning most of the energy stays in the gas rather than turning into light. In that mode, only a small trickle crosses the point of no return, so the glow in radio, infrared, and X-rays stays faint. The difference between quiet and bright is not age, it is access to fuel and the way angular momentum is removed. Gas that falls toward the center still has sideways motion. To move inward, it must shed that spin. Magnetic fields thread the disk and act like a set of gears, moving angular momentum outward so matter can fall in. When the gas supply is rich, this process runs at full speed. When the supply is thin, the fields and turbulence can push as much material out as they pull in. Around Sagittarius A, the balance favors outflow most days. The result is a dim core with brief, low-level flares. Because the average feeding rate is low, Sagittarius A is faint by active galaxy standards. Quasars can outshine entire galaxies for long stretches. If the Milky Way's center fed at that level, our sky would be marked by a bright core, even in daytime. Instead, the core's emissions are modest. The first radio and X-ray detections of the region were weak, and astronomers needed years of careful observing to separate real signals from noise. That faintness delayed a clear picture of the center and forced observers to refine methods that read gravity from star motions rather than from glare. A quiet center carries information. It implies that, for at least the last few million years, the Milky Way's nucleus has had a limited gas supply or a flow pattern that keeps most material from reaching the black hole. Other galaxies show crisp signs of recent outbursts, long jets, radio lobes, and shock fronts that heat the surrounding gas. In our case, large gamma-ray structures called the Fermi bubbles rise above and below the galactic plane. They look like the edges of past outflows. That hint fits with the idea that the nucleus was brighter in the past and is in a calmer phase today. Calm does not mean static. The inner few light years contain young and old stars, stellar winds, compact remnants, and clumps of gas on intersecting paths. From time to time, a packet of gas can move inward, or a star may shed material that drifts close. Observers have seen brief outbursts from Sagittarius A in infrared and X-rays that last for tens of minutes to a few hours. These flares likely mark moments when a small amount of material heats up near the innermost orbits, or when magnetic fields snap and reconnect, releasing energy. After each event, the region settles back into its usual low state. Size alone does not dictate activity. Many very massive black holes are bright because their environments deliver steady fuel. Others with similar mass stay dim in sparse settings. Sagittarius A sits in a crowded but not gas-rich region, and much of the available gas is hot and moving fast, which makes it harder to capture. In contrast, a system like a luminous quasar often lives where cold gas can flow inward along large-scale streams. Cold gas is easier to feed to the center because it can lose energy and settle. That difference in supply helps explain why one nucleus blazes while another rests. The low glare near Sagittarius A makes some measurements easier. It lets astronomers separate individual stars close to the center and follow their orbits with high precision. It also means small brightness changes stand out, so short flares can be tracked in detail. Timing and spectra from these events probe the conditions near the event horizon. They test how turbulence moves energy, how electrons are heated, and how magnetic fields guide the flow. Because the timescales near a 4 million solar mass black hole are minutes to hours, instruments can watch full rise and fall cycles within a single night. Even at low activity, The core emits steady radio waves and occasional X-ray and infrared flares. The radio emission likely comes from hot electrons moving in magnetic fields near the inner flow. X-ray flares can arise when regions of gas get compressed and heat rapidly, or when particles are accelerated to very high energies. Infrared flares trace hot spots that brighten and fade as they orbit close to the hole. By comparing the timing and color of these signals, teams infer where in the flow the energy is released and how fast the material is moving. The patterns point to orbits only a few times larger than the event horizon, where gravity is strongest. The present quiet phase may be part of a cycle. The center can stay dim for long periods and then brighten when a cloud or a stream delivers fuel. Astronomers watched a cloud nicknamed G2 approach the core a few years ago. Some forecasts expected a strong flare. As G2 neared closest approach, it stretched into a thin strand under tidal forces, and much of it kept moving past the center. The brightening was mild. The lesson was practical. A close pass does not guarantee a feast. Gas can be too hot, too fast, or too diffuse to settle. Still, a larger or colder cloud could behave differently, lose energy, and feed a stronger episode. Future activity could also be driven by larger scale changes. On billion-year timescales, galaxy interactions stir gas and send some of it inward. The Milky Way and the Andromeda Galaxy are on a slow collision course. When they merge, their gas will be squeezed and channeled toward the new center, and the combined central black hole will likely experience a period of higher feeding. The details will depend on how much cold gas survives the interaction and how turbulence and magnetic fields move angular momentum. After a bright phase, the system may quiet again as the new galaxy settles. The level of activity connects to habitability in a broad sense. Intense radiation from an active nucleus can change the chemistry of gas clouds and, in extreme cases, strip atmospheres from planets near the center. Earth is far from Sagittarius A, so direct risks at our distance are low, but the overall rate of star and planet formation in the inner galaxy can be shaped by how often and how strongly the core feeds. A quiet center allows gas to cool and form stars more steadily. A bright phase heats and disperses gas, slowing star birth for a time. Over billions of years, these cycles help set the pattern of where and when stars form. The near-term behavior of Sagittarius A depends on local supply. Stars in the central region mostly follow stable orbits that keep them away from the event horizon. Stellar winds from hot, young stars provide a slow, hot drizzle of gas. Supernovae and collisions can stir the region and nudge material inward. Dynamical processes can scatter stars and compact objects into lost cone orbits paths that lead close enough for a star to be torn apart or for a remnant to merge. These are rare events on human timescales, but steady over cosmic time. Each one delivers a pulse of fuel and a brief spike in brightness. Measurements continue to refine the picture. High-resolution radio arrays time rapid variations to set size limits. Infrared instruments watch for flares and map their color changes, which trace temperature and particle energy. X-ray observatories catch the highest energy events. Polarization measurements, the direction of light's electric field, reveal how magnetic fields are arranged near the center. Together, these methods build a consistent model of a hot, magnetized, low-rate inflow with outflows that carry much of the energy and mass back outward. The physics stays simple in outline. Gravity pulls inward. Pressure, rotation, and magnetic fields push outward or sideways. For matter to reach the event horizon, angular momentum must move outward through the flow. When gas is scarce and hot, that transport is inefficient, and outflows remove much of the material before it can fall in. When gas is abundant and cool, transport is efficient, and the inner disk glows. Sagittarius A sits in the first regime most days. Its faint average output is the natural result of a weak and inefficient supply chain. If a true feeding episode begins, say from a dense cloud reaching the capture zone, the core would brighten by large factors. The radio image would sharpen as the inner flow densifies. Infrared light would rise as hotspots form an orbit close to the hole. X-rays would spike as particles heat and accelerate. None of this would be harmful at our distance, but the view from Earth would change. The galactic center would stand out more clearly on dark nights, and instruments would record stronger signals across the spectrum. Such an episode could last for months to years, then taper as the supply thins. On the scale of a galaxy's life, black holes are patient. They can remain dim for long stretches, and then, given fuel, shift quickly into an active state. Evidence from other systems shows multiple cycles across billions of years. The Milky Way likely followed that pattern. Brighter phases in the past, quiet in the present, and brighter phases again in the distant future. The current lull is not an exception to the rules of black hole feeding. It is a normal outcome of a low supply and a flow that prefers to heat and expel gas rather than to radiate it away and swallow it. The quiet core has made possible the cleanest gravity tests near a supermassive black hole, using the orbits of nearby stars. It also offers a way to study accretion at very low rates, a regime that exists in many galaxies today. By watching flares rise and fall, measuring polarization, and timing changes across wavelengths, observers learn how hot plasmas behave in strong gravity and how magnetic fields shape the final steps before matter crosses the horizon. Each small flare is a controlled experiment written by nature, and each quiet night is a baseline that helps reveal the next change. In this setting, comparisons with brighter systems keep the context clear. A quasar's disk reaches a balance where inflow, heating, and radiation drive strong light and strong winds. Sagittarius A sits far below that balance point. The same equations apply, but with different inputs. The mass sets the size and timescales. The fuel sets the brightness. The fields and turbulence set how much of the gas can lose angular momentum and cross inward. Today, the inputs yield a low, flickering output. Over long times, the inputs can shift, and the output will follow. Sudden flares near Sagittarius A interrupt the usual dim glow with short, sharp bursts that rise and fade on human timescales. They arrive without warning, so teams keep flexible schedules and automated alerts to pivot instruments within minutes. The first brightening events surprised observers because the light climbed and fell far too quickly to come from a large region. Timescales of tens of minutes to a couple of hours imply a source no bigger than a few light minutes across, comparable to orbits just a handful of Schwarzschild radii from the center. That immediately placed the action close to the event horizon. Several mechanisms can make such flashes. One path is a clump of gas carried inward by chance. The inner flow around Sagittarius A is hot and thin most days, which keeps it faint, but a denser knot can briefly raise the feeding rate. As it plunges inward, friction and compression heat the gas to tens of millions of degrees. Electrons accelerated in magnetic fields radiate in infrared and X-rays, so the flux jumps and then fades as the clump smears out and cools. Another path is magnetic reconnection, when twisted field lines snap and realign, releasing stored magnetic energy in a fast burst. Reconnection is common in solar flares. Near a black hole, it has more room to run because gravity packs the plasma tight and speeds up the dance. A third idea invokes close passages of stars or compact objects that strip and feed small streams of gas. No single mechanism fits every flare, and the data suggest more than one mode is active. Flares tend to show up most clearly in infrared and X-ray light because the electrons involved reach very high energies. In visible light, the inner region stays faint, and dust along the line of sight absorbs much of the optical signal. To catch the full story, observers build campaigns that combine many wavelengths at once. Radio arrays watch the base level and any slower structural change. Infrared cameras time the fast rise and decay. X-ray satellites catch the hardest photons. When a trigger fires an infrared spike, for example, coordinated observations roll across the spectrum to follow the evolution from minutes to hours. One of the strongest events on record came in 2019, when the infrared brightness briefly jumped to more than twice the prior peak. For a time, some wondered if a star had been torn apart. Follow-up favored a large, hot clump, possibly linked to the G2 cloud that had stretched and passed near closest approach not long before. Other clues also point to brighter phases in the recent past. Faint X-ray echoes from nearby molecular clouds imply that centuries ago, the nucleus shone orders of magnitude above today's average. Close to the event horizon, magnetic fields shape what we see. The plasma near Sagittarius A is threaded by fields that the flow drags and twists. The fields do not come from the black hole itself. They live in the moving, ionized gas. In strong turbulence, the loops tangle, merge, and fragment. Where the field is tight and ordered, charged particles follow helical paths and radiate synchrotron light. Where the field is tangled, the flow can stall or redirect. In some states, the field becomes so strong relative to the inflowing gas that it partially chokes the accretion, a regime called a magnetically arrested disk. Polarized light carries the imprint of field geometry. The Event Horizon Telescope added polarization to its high-resolution images of the galactic center, showing swirl patterns in the dim ring around the shadow. Those patterns imply ordered fields near the innermost orbits and confirm that magnetism is not just a background player. During flares, the polarization angle and degree change as hotspots form and move, letting researchers infer orbital periods close to the last stable paths and test how the flow threads the horizon. The natural size scale is set by the Schwarzschild radius, the radius of the event horizon for a non-spinning black hole. For a mass of about 4 million suns, the radius is roughly 12 million kilometers, about 7.5 million miles, just over 17 solar diameters across. The horizon is not a surface, it is a boundary in space-time. Nothing crossing it can send a signal back out. Just outside, space is already falling inward. Time dilation becomes strong. To a distant observer, clocks near the horizon appear to slow, and light shifts toward the red as it climbs away. Imaging such a small target at such a great distance required extreme resolution. Radio interferometry links far-flung dishes with atomic clocks so that their signals can be combined after the fact. The technique, very long baseline interferometry, measures tiny differences in arrival time from the same wavefront at each station. With baselines as large as Earth, the resolving power reaches tens of microarcseconds, small enough to probe the apparent size of the shadow. Earlier arrays showed that Sagittarius A was compact. The next step was to outline the silhouette itself. Sagittarius A posed a special challenge compared with the first black hole the EHT imaged, the one in M87. M87's black hole is much bigger, so changes near its horizon unfold over days. Sagittarius A is smaller, so comparable orbital periods are minutes. During a single night, the brightness pattern around the ring can morph several times. Standard imaging methods assume a static source. Here, the target evolves while you watch. Analysts built algorithms that slice the data into short intervals, reconstruct images for each slice, and then average them carefully to avoid erasing real motion. Interstellar scattering adds another layer. Turbulent electrons between us and the galactic center slightly refract radio waves, smearing the image and adding speckles that drift with time. At long wavelengths, this blur dominates, but at 1.3 millimeters, it is smaller still present, but correctable. Teams modeled the scattering using observations across wavelengths and removed its imprint statistically, similar to deblurring a photograph with a known point spread function. Closure quantities, combinations of phases and amplitudes that cancel station-based errors anchor the solution when the atmosphere misbehaves. Absolute numbers turn angles into sizes. From Earth, the expected angular diameter of Sagittarius A's shadow is about 50 micro-arcseconds, roughly the size of a baseball on the surface of the Moon seen from here. The EHT's resolving power at 1.3 millimeters reaches that scale when baselines span much of the planet. Each station logs to a hydrogen maser clock and records data at gigabits per second. After the observing run, hard drives from places as distant as the South Pole and the Atacama Desert are flown to correlation centers, where specialized hardware combines the streams into a single, Earth-sized aperture. While imaging forged a direct view of the shadow, other observatories kept watch on the variable glow. Chandra tracked X-ray flares and measured their spectra. XMM Newton added longer, continuous views. New Star extended sensitivity to harder X-rays. In the infrared, Keck and the Very Large Telescope timed fast brightenings and polarization swings. At submillimeter bands, ALMA and the submillimeter array monitored flux changes that often lag or lead the infrared by minutes, offering clues to particle cooling and expansion. Magnetic structure at the horizon matters for outflows. When fields choke the inner flow, inflow piles up against strong vertical strands until reconnection or instabilities let material slip through. That stop-and-go behavior can power episodic ejections and brief boosts in brightness. Sagittarius A shows hints of this regime at low levels. Short radio features and polarization angles suggest ordered fields threading the innermost region, even if no large jet is present today. The geometry of orbits near the horizon sets characteristic times. For a non-spinning 4 million solar mass black hole, the innermost stable circular orbit has a period of about half an hour, as seen from far away. Spin moves that orbit inward and shortens the period for prograde motion. Several infrared flare sequences show quasi-periodic substructure on tens of minutes, consistent with compact hotspots tracing a few orbits before cooling and shearing apart. Polarization rotating during those minutes supports the picture of orbiting knots rather than static patches. Fast variability also constrains size through light-crossing arguments. If a flare doubles and halves within 10 minutes, the region that changes cannot be larger than 10 light minutes across. Otherwise, different parts would respond at different times and smear out the change. For Sagittarius A, such limits point to radii a handful of times the Schwarzschild scale. Those numbers tie the rapid-fire infrared and X-ray spikes to the same compact zone, that the EHT resolves statistically, linking timing and imaging. Behind the scenes, analysis has to guard against false patterns. The atmosphere introduces phase noise that can mimic structure, and instrumental gains drift. To test robustness, teams split the data by time, by stations, and by frequency subbands, then repeated the reconstructions. They also injected synthetic signals into the raw streams to make sure pipelines can recover known answers. Independent groups used distinct imaging philosophies, regularized maximum likelihood, Bayesian sampling of geometric models, and closure-only methods, and compared results. The Schwarzschild solution gives the basic radius, but real black holes can spin. Spin changes the silhouette slightly. The shadow shifts, and the photon ring brightens on the side where material moves toward us. It also sets how close stable orbits can be, and how efficiently the disk can convert gravitational energy into radiation. Current images of Sagittarius A are not yet sharp enough to fix spin tightly, but combining the ring size with flare timing and polarization already narrows the allowed range. Because Sagittarius A changes within an observing night, the EHT in this case works like a high-speed camera with very long exposures. Analysts slice the data into shorter intervals, reconstruct images for each, and then average them with care to keep true motion from washing out. The resulting ring is therefore a time average picture of a living system. In contrast, the M87 image could be treated more like a portrait because the structure evolved more slowly. Even the baseline faint glow contains structure. The average radio spectrum curves in a way that points to a transition from optically thick emission at longer wavelengths to optically thin emission at shorter ones. That turnover marks where the flow becomes transparent, giving a handle on density and temperature. Scattering by interstellar electrons along our line of sight blurs the image at longer wavelengths. Moving to 1.3 millimeters reduces that blur, a key reason the EHT works at that band. New pushes towards 0.87 millimeters aim to sharpen the picture further if weather and sensitivity allow. All of this rests on precise timekeeping. Dishes separated by oceans compare signals using ultra-stable clocks. The path delays through the atmosphere must be modeled and corrected. Each station's position is known to centimeters, and even tiny thermal expansions of structures are tracked. When everything lines up, the array acts as one eye. The payoff is an image of a ring smaller in angle than a donut on the moon seen from Earth, assembled from harmonized beats of radio waves that left the galactic center at the same instant. Beyond the horizon lies the region we cannot sample. Classical general relativity predicts that all paths lead to a singularity, a place where density and curvature diverge, and the equations are incomplete. Quantum ideas suggest the core might be softened or replaced by new physics, but any such details are hidden. No signal from within can reach us. What we can test are the conditions just outside, how plasma orbits, how quickly time passes, how light bends and polarizes, and how magnetism and turbulence move energy. Campaigns now aim to catch flares with the full toolkit running. A typical plan starts with near-infrared monitoring to spot a rise, then triggers follow-ups at X-ray and radio bands. Polarimeters watch for swings in angle. VLBI tracks any structural ripples. The data feed models that compute spectra and light curves for hotspots, reconnection sheets, and magnetically arrested flows. When a model reproduces timing, color, and polarization together, confidence grows. When it fails, parameters are revised and new runs begin. The same methods also look backward in time using light echoes. Dense clouds near the center can act like screens. If the core brightened greatly in the past, Some of that light would reflect or be re-emitted later, with a delay set by geometry. X-ray maps show knots and filaments lit as if by a moving spotlight. By measuring the spectrum and timing of those echoes, teams infer how bright the core was centuries ago and how long the bright phase lasted. Reconstructions suggest that Sagittarius A has cycled through higher states within the last few hundred years. At sub-millimeter wavelengths, variability on timescales of tens of minutes likely traces orbital motion near the innermost stable circular path. In some sequences, the polarization angle rotates during a flare, as expected if a compact hotspot circles a few times before fading. The period of that rotation limits the radius and, in turn, can constrain spin if the viewing angle is known. In other cases, the timing favors reconnection that accelerates electrons in a sheet that then cools. A mix of both behaviors is likely, changing with supply and field geometry. Understanding these events depends on the microphysics of collisionless plasmas. Near the hole, particles rarely collide. Fields and waves exchange energy instead. How electrons are heated relative to ions matters because electrons radiate the light we see. If electrons take only a small share of the heat, the flow stays dim, even when mass moves inward. If reconnection or shocks dump extra energy into electrons, a brightness spikes. Particle in cell simulations track this process in simplified patches and help translate flare data into physical conditions. As methods refine, the flares become laboratories for strong gravity and plasma physics in one place. The sharp bending near the horizon can, in principle, lens a bright knot into multiple images separated by tiny delays. Detecting such substructure would probe the space-time metric more directly. Polarization swings map magnetic topology. Spectral slopes track how electrons are heated. Time lags between infrared and submillimeter light follow cooling and expansion. Each flare is a compact experiment written by nature and timed by the deep clock set by mass and spin. At the center of all of this is the simple radius scale that sets expectations. A Schwarzschild radius of about 12 million kilometers translates to an angular half diameter of roughly 25 microarcseconds at 26,000 light years. Add bending, and you get a shadow diameter near 50 microarcseconds. The measured value sits at that scale. The agreement between dynamics from stellar orbits and geometry from the shadow ties mass to image in a way few other systems allow, cross-checking two very different ways of weighing the same object. In 2017, the Event Horizon Telescope aimed its full network at the Milky Way's center and recorded an enormous haul of raw signals. The source changed while they watched. Gas close to the event horizon moved at a large fraction of light speed, so the brightness pattern shifted in minutes. That meant the data could not be treated like a single long exposure. After the observing run, crates of hard drives went to correlation centers. There, atomic clock timestamps from each site were aligned so that wave crests recorded in Chile, Hawaii, Mexico, Europe, and the South Pole could interfere properly. Correlation is the step that turns many telescopes into one virtual dish. Calibration follows, removing instrumental gains, atmospheric delays, and small phase errors. Only then can imaging begin. Gaps in the virtual telescope remain because Earth does not hold radio dishes at every longitude and latitude. Those gaps make the inverse problem hard. Rather than take a picture, teams solve for an image that matches the measured interference patterns while staying physically reasonable. To avoid bias, the collaboration split into independent groups that did not share results until the end. Each group used different starting assumptions and different algorithms. Some favored geometric models, others used regularized images that balance sharpness and fidelity. When the blind reconstructions finally met, the ring features lined up within uncertainties. The match gave confidence that the image features were set by the sky, not by the code. In 2019, the first public image from the project was not the Milky Way's core, but the black hole in M87. That choice had practical reasons. M87's black hole is billions of solar masses, making its shadow large on the sky. Its inner flow changes more slowly, so one night's data are closer to a snapshot. Even at that scale, the image was a challenge, yet the ring emerged, a bright, asymmetric halo around a dark center. The asymmetry fits expectations, since material moving toward us appears brighter due to relativistic beaming. The result was a direct test of general relativity in a strong field regime, using the way space bends light near an event horizon. Sagittarius A demanded new methods because it evolves quickly. The same path that worked for M87 would blur a ring that keeps changing. Analysts built movie-aware pipelines. Instead of solving for one static brightness map, they solved for a time series, many short frames that, together, match the data. Another approach generated very large ensembles of plausible images and then looked for common patterns, a way to average without washing out real motion. Simulations helped guide expectations by showing how hotspots, turbulence, and magnetic strands would paint the ring at 1.3 millimeters. When the final reconstructions were released in 2022, they showed a thicker, fuzzier ring than M87's, with size and brightness consistent with a 4 million solar mass black hole at the known distance. Why the fuzz? Two reasons dominate. First, the target morphs while the array is collecting data. Second, interstellar scattering caused by turbulent electrons between us and the center adds a small, shifting blur. The teams measured that blur at other wavelengths and subtracted its effect statistically. They also used closure quantities, combinations of signals that cancel station-based errors, so the final picture rests on the most stable parts of the data. Even so, the end product remains a time-averaged view of a living system. It is not a single instant, but it is anchored by repeated, independent reconstructions. The image opened new questions rather than closing them. Spin sits high on the list. A black hole's spin sets how close stable orbits can be, how efficiently the disk converts gravity into light, and how easily magnetic fields can launch outflows. The ring's overall size nails down mass combined with distance, but spin mainly tweaks the ring's brightness pattern and small asymmetries. In Sagittarius A, those patterns are smeared by motion during an observing night and by scattering. That is why additional tools are needed. Orientation is another unknown. M87 offers a bright jet as a compass. Sagittarius A does not show a large, steady jet, at least not in current images. Weak outflows may exist but are hard to pull from the crowded and dusty scene. Without a visible axis, the tilt must be inferred from subtle clues. The way polarization swings during flares, the timing of hotspots as they orbit, and the ring's slight brightness imbalance. Each clue carries uncertainty on its own. Together, they narrow the options. Polarization adds leverage because it tracks magnetic fields. Light is an electromagnetic wave, and in many environments, the wave's electric field lines prefer certain directions. Scattering, synchrotron emission from spiraling electrons, and passive passage through magnetized plasma, all imprint patterns. Near Sagittarius A, the Event Horizon Telescope's polarized data show a whirl pattern around the ring, evidence that ordered fields thread the inner flow. During flares, the polarization angle can rotate over tens of minutes, as if a compact bright knot is orbiting. The period of that rotation gives an orbital timescale, and therefore a radius. If the viewing angle is known, those radii can tie back to spin. X-ray polarimetry offers a different angle on the same physics. As matter falls inward, it heats and emits X-rays. In curved space-time, spin drags the local frame, a phenomenon called frame dragging, so that paths and scattering geometries twist. The polarization of outgoing X-rays carries a faint record of that twisting. NASA's Imaging X-ray Polarimetry Explorer, launched in 2021, can detect polarization in bright events. Sagittarius A is faint in X-rays most of the time, but flares lift it above threshold. By catching a flare and measuring the polarization fraction and angle, IXPE can test models of the inner flow and, in combination with timing, limit the spin. Other instruments add necessary pieces. Gravity at the Very Large Telescope Interferometer can measure tiny shifts in the infrared light centroid during flares, tracking hotspots as they orbit and shearing into the flow. Those astrometric loops have sizes and periods that map to radii a few times the event horizon. Near-infrared spectroscopy measures Doppler shifts as the spots move toward and away from us, turning loops into orbits with direction and speed. On the radio side, multi-frequency monitoring tracks how flare peaks at different wavelengths, lead or lag, a clue to how electrons cool and how emitting regions expand. Pulsars would be a prize. A pulsar is a rapidly spinning neutron star with a lighthouse-like beam. If a pulsar orbits close to the black hole, the timing of its pulses would carry razor-sharp tests of gravity and spin. Very sensitive surveys have searched for such pulsars near the center. Scattering by intervening plasma smears the pulsars at low radio frequencies, making them hard to find, but higher frequency searches continue. A single close pulsar could weigh the black hole and measure spin far more tightly than current methods. The EHT itself is growing. Adding more stations fills gaps in the virtual aperture, and higher recording rates raise sensitivity. Weather always limits the shortest wavelengths, but pushes towards 0.87 millimeters promise finer detail when conditions align. Space-based radio antennas would help even more by creating longer baselines and by filling coverage from orbits no ground site can reach. Concepts for space-ground interferometry at sub-millimeter bands are being studied for the longer term, with the goal of turning time-averaged rings into true movies. All of the image work depends on precise clocks and careful logistics. Hydrogen maser clocks keep each station's time stable to parts in a quadrillion. Engineers model the travel time through the atmosphere above each dish and adjust for small changes with water vapor radiometers and meteorological data. After observing, teams fly hard drives to correlators because the data volume is too large for the public internet. The hardware there multiplies, delays, and combines streams so that a single wavefront is reconstructed. Tests with synthetic data check that the full pipeline can recover known images, a guard against algorithmic bias. While imaging advances, the broader context continues to build from multi-wavelength campaigns. Chandra, XMM Newton, and NuSTAR watch for X-ray flares and measure their spectra. Keck and the Very Large Telescope track infrared flares and polarization. ALMA and the Submillimeter Array measure submillimeter variability and polarization that often change on slightly slower clocks. When a flare appears, alerts move quickly. and telescopes pivot to catch overlapping views. The timing between bands, the color changes within each band, and the polarization swings together place strong limits on where energy is released and how electrons are accelerated. Light echoes in nearby molecular clouds add a stand-in for history. X-ray brightening that sweeps across these clouds can be used like a mirror with a time delay. By modeling the geometry, teams turn echo patterns into a record of past outbursts. This record suggests that our nucleus was more active centuries ago. If so, the Fermi bubble's huge lobes of gamma-ray emission above and below the plane may be relics of an older wind, now cooling and fading. Imaging the ring today while reading these echoes gives both the present tense and a partial past tense of the same engine. At the scale of the ring, gravity dominates, but microphysics matters. The plasma near the horizon is collisionless, so particles exchange energy through fields and waves, not through frequent collisions. How electrons are heated relative to ions sets the brightness. If electrons get only a small share of heat, the flow stays dim even with mass moving inward. Magnetic reconnection can temporarily dump extra energy into electrons, producing fast, bright flares. Particle and cell simulations, which compute field-particle interactions in small patches, help translate observed spectra and light curves into temperatures, densities, and acceleration efficiencies. Schwarzschild's solution gives a clean radius for a non-spinning hole, but real holes likely spin. Spin moves the innermost stable orbit inward for material rotating in the same direction and outward for the opposite. It shifts the shadow slightly and brightens the approaching side of the ring. With time-resolved imaging, polarization, and infrared astrometry together, constraints tighten. Even without a perfect number today, the allowed range is shrinking as data accumulate and as algorithms improve at teasing signal from a target that refuses to sit still. None of this calls for exotic departures from general relativity at the radii we can probe. The ring size matches the mass measured from stellar orbits. The way light bends fits the standard predictions. The challenge is not a failure of the theory, but the practical task of measuring a fast, faint, scattered, and evolving source with a network of telescopes scattered across the planet. The solution's better baselines, faster recording, smarter algorithms, and more coordinated campaigns are technical and patient. Work now aims at turning single snapshots into sequences, shorter integration times, wider bandwidths, and more stations improve frame-by-frame reconstructions. If a bright hotspot or a reconnection sheet can be tracked around the ring for a few orbits, the period directly gives a radius. With a known mass, that radius becomes a test of spin. Polarization following the same feature maps the field geometry and shows how ordered or tangled the inner flow is. Coordinated X-ray and infrared coverage adds the energy budget, telling how electrons are heated and how quickly they cool. The image of Sagittarius A was a milestone in technique, but the target continues to require new thinking. Methods that worked for a stable portrait had to be rebuilt for a flickering scene. The result is a ring that agrees with basic expectations and a toolkit that can watch it change. As more observing runs add data, and as overlapping instruments pin down timing and polarization, the core properties spin, tilt, and the state of the inner flow come into sharper focus, one carefully cross-checked piece at a time. Plans for the next observing cycles push the Event Horizon Telescope from single portraits toward true time-resolved imaging. More stations on Earth will fill gaps in the virtual aperture dishes in Africa to improve east-west coverage, sites in the mid-Pacific for north-south baselines, and higher, drier locations to beat atmospheric water vapor. Wider bandwidths and faster recorders raise sensitivity. phased arrays, which tie many small dishes into one effective antenna, make faint structure detectable. Running at multiple submillimeter wavelengths at the same time will show how different layers of the flow heat and cool, so a flare can be tracked as it lights up first in the infrared, then at 1.3 millimeters, and finally at longer bands as electrons cool and the emitting region expands. Concepts extend off the planet as well. A sub-millimeter dish in orbit, phase-locked to the ground network, would add baselines impossible from Earth alone. Those extra spacings sharpen resolution enough to turn a time-averaged ring into a short movie. Hotspots forming and fading, brightness asymmetries sliding around the ring with orbital times of tens of minutes. Polarization vectors, rotating as magnetic loops, twist and reconnect. Space-ground interferometry also steps over some weather limits and can sample more hour angles in a single day, improving the UV coverage that imaging algorithms need. Upgrades target polarization just as much as total intensity. Polarization traces magnetic order near the event horizon. Simultaneous polarimetric imaging at 1.3 millimeters and 0.87 millimeters will map how field geometry changes during flares. If the inner flow enters a magnetically arrested state where strong vertical fields partly choke, the inflow polarization patterns should grow more ordered and then scramble as reconnection releases stored energy. Cross-checks with near-infrared polarization from large telescopes on the ground add a second layer, linking radio-bright regions to infrared-bright hotspots. Beyond light, the next messenger is space-time itself. Gravitational waves are ripples produced when massive objects accelerate. A steady supermassive black hole does not radiate strongly. Its curvature is static. To make a measurable wave, the system must change. Two black holes merging, a compact object on a tight, decaying orbit, or a star's core collapsing. Ground-based detectors like LIGO and Virgo hear the high-frequency chirps of stellar mass mergers. Signals from orbits around supermassive black holes are much slower, sitting in the millihertz band that only a space mission can reach. The Laser Interferometer Space Antenna LISA is designed for that band. 3 spacecraft will fly in a triangle millions of kilometers on a side, trading laser beams and measuring separations to picometer precision. Among its targets are extreme mass ratio in spirals, or EMREs, a neutron star, or a stellar mass black hole captured by the gravity of a supermassive one, shaving off energy over tens of thousands of orbits until it plunges through the horizon. Each swing encodes the mass and spin of the central object in exquisite detail. The waveform is a long, slowly rising song whose harmonics depend on the exact shape of space-time. If such a source orbits near Sagittarius A, LISA would recover the mass to tiny fractional errors and place tight limits on spin and tilt. Even if the source is elsewhere in the universe, the same physics applies, and combining LISA's parameters with images, polarization, and infrared astrometry at the galactic center would bind together 2 independent ways of reading strong gravity. Gravitational waves slip through matter almost untouched. They are not scattered by dust or bent by plasma. That property makes them ideal probes of the region just outside the horizon, where light can be trapped or redirected. Light tells us about temperatures, densities, and fields. Waves tell us about geometry. If either messenger departs from general relativity's predictions, the deviation will be specific. An odd frequency in the ringdown after a merger, or a phase shift in an EMRIS slow chirp that cannot be explained by a Kerr black hole. Most models expect agreement, but testing is part of the job. Far ahead on the calendar, the canvas grows larger. The Milky Way and Andromeda drift toward each other at roughly 110 kilometers per second. In about 4 billion years, they will pass through one another and begin a long process of merging. Stars mostly miss star-to-star collisions because the spaces between them are vast, but orbits change. Spiral patterns blur. Tidal forces draw out long tails. Gas clouds collide and shock, losing energy and sinking inward. Those shocks compress gas and ignite star formation in bursts. Some of that cold gas will funnel toward the common center, raising the feeding rate of the nucleus and switching on activity. As the merger proceeds, each galaxy's central black hole sinks by dynamical friction gravitational drag from stars and dark matter into the deepening potential well. For millions of years, they orbit as a bound pair, hardening as they fling nearby stars away and as gas torques drain energy. Throughout this phase, low-frequency gravitational waves carry off angular momentum. A future space detector would trace the inspiral and the final coalescence, recording a loud, clean signal in the millihertz band. On the electromagnetic side, inflows can light both cores, driving winds and perhaps jets that sculpt cavities and throttle star formation in the inner regions. The remnant of the merger will be an early type galaxy, likely elliptical, its old spiral disks transformed into a rounder, more random stellar system. The central coalescence ends with a single, heavier black hole. The final mass depends on the masses that went in and on how much gas was swallowed during the last stages. If the spins of the two holes are misaligned, the merger can impart a recoil kick to the remnant. In most giant systems, that kick is not enough to eject the black hole, but it can displace it for a while, setting up oscillations before the remnant recenters. The spin of the new hole records the history. Orbital angular momentum, individual spins, and accreted gas all contribute. That spin then sets the efficiency of future accretion and the ease with which magnetic fields launch outflows. At human distances from the center, the consequences are gentler. Night skies change slowly as Andromeda swells, first as a smudge, then as a broad band cross-hatching our own. Constellations distort over millions of years. Star formation flares in waves where gas compresses. Then it fades as fuel is used or heated. For planets far from the core, the radiation from an active nucleus is diluted by distance. The larger risks for habitability in our neighborhood will come from the sun's evolution, rising luminosity over the next 1 to 2 billion years, a moist greenhouse phase that can drain the oceans, and a red giant stage about 5 billion years from now that will strip or engulf the inner planets. Those timelines bracket the merger. They also remind us that cosmic changes are measured in very different units than human ones. Closer to the present, practical steps keep stacking up. Gravity, the infrared interferometer at the Very Large Telescope, measures astrometric wobble during flares with micro-arcsecond precision, turning brightness changes into tiny loops on the sky that trace near-horizon orbits. IXPE, the X-ray polarimetry mission, waits for bright flares to measure polarization fraction and angle, looking for the subtle twist that frame dragging and strong curvature imprint. ALMA and the submillimeter array watch flux and polarization at submillimeter bands, catching lags between wavelengths that indicate electron cooling and expansion. Keck and the VLT take spectra during flares to measure Doppler shifts and therefore orbital speeds and directions. When a trigger fires in one band, alerts flow to the others, and the instruments pivot. On the radio interferometry side, adding EHT stations fills missing angles in the virtual aperture, which reduces artifacts and shortens the time needed for a single frame. That matters because Sagittarius A evolves in minutes. Higher recording rates and better receivers push downward in integration time without sacrificing sensitivity. Working at 0.87 millimeters, when weather allows, will shrink interstellar scattering further and sharpen the ring. Space partners would lengthen baselines and tune the geometry so the array samples more unique spacings, making the inversion from interference patterns to images less ambiguous. Data handling scales with ambition. Each station's hydrogen maser sets time with parts per quadrillion stability. Petabytes of data cross oceans by airplane because public networks cannot carry the load. Correlators align wavefronts to picoseconds. Algorithms solve for both images and motion at once, using priors informed by simulations but constrained by closure quantities that cancel out many calibration errors. Blind imaging teams still proceed independently and compare only at the end. Synthetic data with known answers still flow through pipelines as a guard against bias. These practices discipline, replication, careful error budgets turn a hard inverse problem into a robust result. Complementary fossil records continue to add context. X-ray light echoes sweep across nearby molecular clouds with delays set by geometry, implying that the core was far brighter a few centuries ago. Radio maps show faint, balloon-like structures and filaments, signatures of older winds and outflows. Gamma-ray images reveal the Fermi bubbles rising tens of thousands of light-years above and below the plane. Each dataset is an entry in a long ledger of activity. Quiet now, brighter then, and likely bright again at some future date when fuel arrives. Numerical models are keeping pace. Global simulations now combine general relativity, radiation transport, and plasma physics. They produce rings, polarization maps, and flare statistics that resemble observations. Within those global runs, local particle-in-cell models follow reconnection and electron heating to build recipes for how energy is partitioned between electrons and ions. Those recipes feed back into the larger codes, closing a loop between microphysics and the behavior of the whole flow. The emerging picture for Sagittarius A is a hot, magnetized, low-rate accretion state, often near the magnetically arrested regime, punctuated by short, reconnection-driven brightenings. Over galaxy scales, supply and feedback set the cadence. Cold streams, minor mergers, and stellar mass loss deliver gas inward. Bars and spiral arms torque it, moving angular momentum so that some fraction can sink to the center. Outflows from the nucleus heat and stir that same gas, lifting part of it back to larger radii. The cycle accumulation, ignition, outflow, rest, repeats on timescales of millions to hundreds of millions of years. The Milky Way appears to sit in a resting interval. Polarized rings and faint flares are its present tense signature. Bubbles and echoes are its recent past. Core measurements remain the anchors that everything else ties to. Stellar orbits weigh the mass directly. The EHT ring diameter cross-checks that mass through light-bending geometry. Polarization vectors sketch magnetic order at horizon scales. Flare timing sets sizes and orbital periods near the inner edge of stable motion. X-ray spectra mark the hottest electrons and the depth of gravitational redshift. When available, gravitational waves will map spacetime with no reliance on intervening matter. Agreement among these independent probes turns inference into measurement. Practical progress looks incremental from year to year. One more station online, one more bandwidth upgrade, one more calibration trick, But the compound effect is large. Shorter snapshots make it feasible to see structure evolve around the ring in real time. Better polarimetry clarifies how fields regulate inflow and trigger flares. Multi-wavelength coordination nails down where and when electrons are heated. Space interferometry would lift resolution enough to watch hotspots complete orbits, rather than infer them. LISA will extend the listening to the slow rhythms of massive orbits and mergers. Together, these steps turn a single, fuzzy silhouette into a dynamic, quantitative probe of gravity and plasma in the strongest accessible field near home. The same rules that govern brighter, more distant quasars operate here, only with lower fuel. Gravity pulls. Rotation and magnetic fields set the gears that move angular momentum. Radiation and outflows carry energy away. When fuel is scarce and hot, most of the energy stays in the plasma, and much of the mass escapes in winds, so the light stays faint. When fuel is cold and abundant, inflow is efficient. The inner disk glows, and the nucleus can reshape its environment. Sagittarius A sits in the first mode today, flickering rather than blazing, but responsive to supply. Its ring and flares are close enough to resolve, slow enough to watch, and faint enough that nearby stars remain visible for dynamical tests. That combination makes the galactic center an unmatched place to refine tools, cross-check theories, and link the physics of a quiet black hole to the engines that power the brightest beacons in the universe.